Hi guys, welcome to the lesson of partial differential equations. So the topic of our discussion is the method of eigenfunction expansion. In the previous classes, we discussed the cosine and sine expansion. Therefore, now we are going to discuss the general Fourier expansion. So here we can see that the Robin boundary conditions are given for the particular heat equation, non-homogeneous heat equation with a heat source. This is heat source, right? So the boundary conditions are Robin boundary conditions. We can see here, this is the weighted sum of the Dirichlet and Newman boundary conditions, right? So initial condition is given as ux of 0 is equals to 0. Now we are going to expand the eigenfunction. So for that, first of all, we are going to find the eigenfunction for this problem using the given boundary conditions, right? So the boundary conditions are u of negative pi comma t minus u of pi comma t is equals to 0, and then ux of negative pi comma t minus ux of pi comma t is 0, right? So here we know that we are going to work for case 3, that is lambda is less than 0. For that, we have lambda is equals to negative p squared, right? Therefore, x of x will be a cosine px plus b sine px. And then the derivative of this function is negative ap sine px plus bp cos px, right? We are going to apply the boundary conditions. The first condition says x of negative prime is equals to, x of negative pi is equals to x of pi. So here we apply the conditions. This a cosine negative pi will be cancelled by a cosine pi because a cosine negative pi is a cosine pi. So both have same sign, and so this will cancel out. And this b sine negative p pi means negative b sine p pi. So when we will shift this on the right hand side, so it will be 2b sine p pi, and this is equals to 0. So p will be equals to n from here because sine inverse 0 is equals to n pi. So this p pi will be equals to n pi, and pi will cancel out. Therefore, we left with p is equal to n. Now we'll apply the second boundary condition, that is x prime of negative pi is equals to x prime of pi. Therefore, we have applied the conditions in the equation, and we get again ap sine pi is equals to 0. Therefore, we get p is equals to n. Now the eigenfunction in this case is x of x is equals to a cosine nx plus b sine nx. So the solution for this heat equation will be given by the Fourier series. We can see that in the previous cases, either a becomes 0 using the boundary conditions, either b becomes 0, right? But here none of these are 0, therefore the Fourier series is generated. So the solution will be given by this summation n is equals to 0 to infinity a n of t cosine nx plus b n of t sine nx, right? So here now for a naught prime, we know that a naught prime will be equals to 1 over 2 pi limit negative pi to pi q of x dx is equals to f naught. All right, so this will be f naught, and then a n prime plus n squared a n is equals to 1 over pi negative pi to pi qx times cosine nx dx. We will call it fn cosine, right? Because this an is the coefficient of cosine series, so we represent by fn c, right? So bn prime plus n squared bn is equals to 1 over pi from negative pi to pi qx sine nx dx, and fn sine because this s represents sine, so right, because this is the coefficient of sine series bn. And then for initial condition a naught of 0 will be equals to 1 over 2 pi negative pi to pi, then initial condition dx, this is initial condition is 0, therefore all these will be equals to 0. A and naught is 0, a n is 0, and b and all are 0, right? So a naught is equals to integral of f naught dt with the condition that a naught of 0 is equals to 0, right? So here we can find a naught, then a n prime plus n squared a n is equals to fn cosine series, and again the condition is equals to 0, right? So these are three initial value problems: a naught, a n prime, b n prime, and we can solve these initial value problems using the initial conditions. So here the solution for this equation will be equals to a, because this is a linear differential equation of first order, therefore the solution will be equals to a n is equals to 1 over e to the power n squared t, that is the integrating factor for this equation, right, times the integral of fnc times e to the power n squared t dt. And for fns similarly, bn is equals to 1 over e to the power n squared t times the integral of fns e to the power n squared t dt. So we will solve these integrals for whatever the function is given, that is the heat source. So if the heat source is given, then we can calculate this fns, fnc, and f0, right? So in this manner, we can generate the solution for this particular problem. That is the problem for Robin boundary conditions. So we see that for Robin boundary conditions, the Fourier, general Fourier series is going to be used. And our previous practice was that in the problems, particularly, we use cosine or sine series, right? But in this case, we are going to use general Fourier series. So now we are going to talk about an example with mixed boundary conditions. All right, so here non-homogeneous heat equation is given with the time independent heat source, and the boundary conditions, we can see that there are mixed boundary conditions. So the method is similar, just we are going to find the eigenfunction for this problem for the given boundary conditions. Therefore, using case 3, that is lambda is equals to negative p squared, we are going to solve this problem by calculating the eigenfunction. So here is the initial condition, this one. We can see that initial condition, and f of x t is equals to t sine 5 pi x over 2 minus sine t pi x over 2 u naught x, that is the initial condition, is equals to sine pi x over 2 plus 2 sine 3 pi x over 2, right? So the eigenfunction satisfying the given boundary condition is xn is equals to a cosine px plus b sine px. And then we need the derivative because the boundary conditions are given. One is simple normal boundary condition, that's Dirichlet, and other is the Newman's condition. So it's the mixture of Dirichlet and Newman, right? So from here we got the eigenfunction, eigen value, that is 2n minus 1 over 2 times pi. Then the eigenfunction will be xn of x is equals to sine 2n minus 1 over 2 pi x. Now this is the eigenfunction. Therefore, we are going to expand the solution in terms of sine, right? Now we are going to find these differential equations, family of differential equation, that is n prime plus 2n minus 1 squared over 4 pi squared an is equals to the integral of function of xt with the eigenfunction, right? So this is the function of xt. We have to integrate with the product of eigenfunction from 0 to 1 for the limits, right? So now we know that this integral, and this is t sine 5 pi x over 2 multiplied by sine 2n minus 1 over 2 pi x. So by the orthogonality, we know that if n is not equals to m for this case, therefore the integral will be equals to 0. And for only n is equals to m, we will get the values. So for n is equals to 2 here, you can see that if n is equals to 2 here, so it will be 3 over 2, right? 3 pi x over 2. So we are going to put n is equals to 2, then we are going to get -1, right? Because here the coefficient of this is -1, this function. And then for this one, we are going to use n is equals to 3, right? So we are going to get t because the coefficient of this is t. So for n is equals to 3, it's t, n is equals to 2, it's -1, and for all other n's, it will be 0, right? Now we are going to construct the differential equation. So a2 prime plus 9 over 4 pi square a2 is equals to -1. A3 prime plus 25 over 4 pi square A3 is equals to t. And then generally n prime plus 2n minus 1 whole square over 4 pi squared an is equals to 0 for all n not equals to 2 comma 3, right? Now finding the initial conditions. So an of 0 is equals to 2 over 1 times the integral of the initial condition times the eigenfunction. And again, here we are going to use a similar idea. If n is not equals to 1 and 2, so the integral will be 0. And for n is equals to 1, we can see that the coefficient of this pi x over 2 is 1. So this is to 1 for n is equals to 1. The integral value is 1, and for n is equals to 2, we have the value of integral as 2, and for all other n's it's 0, right? Now we are going to construct the differential equations. So a1 prime plus 1 over 4 pi squared an is equals to 0, and the condition a1 of 0 is equals to 1. So from this equation, we are going to get a1 by solving it as a linear first order differential equation. So the value of a1 is here, right? And then for a2 prime plus 9 over 4 pi squared a2 is equals to -1, and a2 of 0 is equals to 2. So using the conditions and the equation, we will get a2 as a result 2 plus 4 over 9 pi squared times e to the power -9 pi squared over 40 minus 4 over 9 pi squared, right? So here is a2. And for a3 prime plus 25 over 4 pi squared a3 is equals to t, and the condition is equals to 0. Therefore, we'll get the final result here, right, by solving that differential equation. Then for general an, we know that all other an prime plus 2n minus 1 over 4 squared pi squared an is equals to 0, and the condition is also equals to 0. Therefore, from this differential equation, we will get an is equals to 0. So now the final solution is in terms of this pi x over 2, 3 pi x over 2, and 5 pi x over 2, because we only use these functions and all other an's were 0, right? So in this way, we have generated the final solution using the method of eigenfunction expansion for the mixed boundary conditions. So from the next class, we are going to start the Fourier transform methods for partial differential equations. So we will see how to solve the heat equation using the Fourier transform methods. So I hope you guys will learn from this lesson, and that's all for the time being. Thanks for watching the lesson.